Okay, I want you to imagine, just for a moment, a regular kitchen pressure cooker. You know the exact one I'm talking about, right? It sits on the stove, building up immense heat and steam to cook your food in record time. Now, take that image and scale it up by about 10,000. Picture these massive, towering steel vessels in a refinery or a chemical plant. They're filled with highly volatile, often toxic fluids, and they are operating under extreme temperatures and pressures. So what happens when that pressure builds up just a little too high? Well, in your kitchen, a tiny little valve pops and hisses. But in an industrial plant, if the pressure relief systems aren't engineered to absolute perfection, the entire facility could face a catastrophic explosion. So, welcome to this explainer. Today, we are unpacking the incredible, frankly invisible engineering of industrial safety, specifically looking at how facilities use highly specialized mechanical devices to prevent overpressure disasters. To really understand this, we're going to use API standards 2000, 520, and 521 as our blueprint today. We're going to cover the actual threat of overpressure, the specific pressure relief devices themselves, how engineers mathematically size those relief valves, the rules for safe installation, and finally, disposal systems like flares and drums. Okay, let's dive into this with Section 1, the threat of overpressure, its causes and the stakes. Because honestly, before we can talk about the solutions, we really need to understand the threat itself. Why do these massive, heavily reinforced steel tanks even need venting in the first place?
Well, the standards outline several primary scenarios that cause internal pressure to spike dangerously high, or, and this is just as bad, drop so low that it creates a crushing vacuum. First, you've got simple liquid movement. Just pumping massive volumes of fluid into or out of a tank displaces the vapor space inside. Then you have extreme weather. Imagine a sudden drop in temperature or a heavy rainstorm that can rapidly cool a tank, condensing the vapor inside and instantly creating a vacuum. We also absolutely have to plan for external fire exposure, which essentially boils the liquids inside the tank like a kettle. Furthermore, you've got equipment failures. Think of a choke collapse in an oil well that suddenly unleashes this massive high-pressure flow. And finally, human error during maintenance. This includes things like inadvertently leaving isolation valves closed or steaming out a vessel to clean it, which causes drastic pressure shifts. So you can see the stakes in these industrial operations literally couldn't be higher. So how do engineers actually protect against all these scenarios? API 521 outlines a very strict hierarchy of protection. Step 1, you try to avoid the risks altogether. Maybe you design the vessel to withstand the highest possible pressure from any source. But if that's not possible, you move to Step 2. You rely on engineering controls. And this is exactly where our pressure relief devices come in. Finally, you have administrative controls, like manually locking certain valves open. Notice the crucial emphasis here on engineering controls. While automated instruments and administrative safety procedures are fantastic, they are absolutely not a substitute for physical mechanical pressure relief devices. Think about it. If the power goes out or a computer completely crashes, a mechanical valve is still going to operate.
Let's look at the formal definition of overpressure for a second. It's defined as the result of an unbalance or disruption of the normal flows of material and energy that causes them to build up in a system. So the really crucial takeaway here is that pressure relief engineering is fundamentally this elaborate and complex study of material and energy balances. You have to know exactly how much energy is entering the system, and you have to design a guaranteed way for it to escape. Which brings us to Section 2, Pressure Relief Devices Explained. Let's look at the hardware. We are going to transition now to the physical heroes of our story. These are the mechanical devices that just sit silently on top of these tanks for years, waiting to pop open and save the day. Consider the direct-acting weighted pallet vent valve. It's an incredibly elegant piece of engineering used for low-pressure atmospheric storage tanks. It literally uses the physical weight of the pallet, that flat disc you see sitting over the opening right there, to keep the device closed. The valve remains perfectly, completely sealed until the internal pressure of the tank literally overcomes gravity, physically lifting that heavy pallet off its seat to let the gas escape. Simple, right? And this brilliantly illustrates the next evolution. Because what happens when we need to contain much higher pressures? You can only make a lead weight so heavy before it becomes completely impractical to use. So for higher pressure thresholds, engineers swap those weights out for heavy-duty springs. A spring-loaded pressure relief valve uses a compressed spring to push down on the disc. When the system pressure exerts a force greater than the spring's preset tension, bam, the valve is forced open. And once the pressure drops back down to a safe level, the spring snaps it right shut again. Now let's look at a much more advanced piece of hardware, the pilot-operated vent valve. Unlike the direct-acting valves we just looked at, these are soft-seated for premium tightness. Here is the really genius part.
the top of the internal piston actually has a larger surface area than the bottom. Because of this, the process pressure actually works with the valve to hold it shut. The force holding the seat closed actually increases as the internal pressure rises. It is literally tightest right up until the exact moment it needs to open. At that specific set point, a tiny external pilot valve pops open, venting the pressure from the top dome, which suddenly reverses the forces and allows the main massive valve to fly open. It is such a cool mechanism. But before we move on to the math, you definitely need to know about a concept called simmer. This is the audible or visible escape of fluid between the seat and the disc that happens just below the set pressure, right prior to fully opening. You can kind of think of it as the warning hiss of the valve. It's basically telling the operators, hey, the system is right at its absolute limit, and I am about to fully pop open. All right, let's move to section 3, sizing the relief valves. The math. How do engineers actually calculate the exact size of these valves so they can handle the massive flows required during an emergency? Because if the valve is even a little too small, the tank will still rupture. Well, the very first step is knowing exactly what you are venting. API 520 dictates that valves must be tailored with specific trims depending on their relief medium. Ask yourself, are you venting pure gas, pure liquid, or maybe a chaotic, completely turbulent two-phase mixture of flashing liquid and vapor? You absolutely have to select the appropriate trim, otherwise the valve might become unstable. It could end up fluttering open and closed violently, basically destroying itself in the process. Now, when sizing these valves for gases, engineers have to determine if the flow is subcritical or critical. In subcritical flow, the pressure downstream in the discharge pipe kind of acts as a bottleneck, affecting exactly how fast the gas can escape. But in critical flow, the pressure difference is so extreme that the gas actually reaches the speed of sound as it exits the nozzle. Think about that for a second. At that point, flow reaches a maximum velocity. It literally cannot go any faster, meaning downstream pressure no longer restricts the flow rate at all. Knowing this is absolutely vital to choosing the right sizing formula. Now, what's really interesting about this slide is how engineers actually figure this out. While these precise API curves might look a bit intimidating, engineers rely on them every day to find exact mathematical correction factors, like the F2 values shown here. Every single gas has a different specific heat ratio, and these curves allow the engineer to pinpoint exactly how that specific gas will behave under critical or subcritical conditions. It saves them from having to do incredibly complex calculus on the fly. Ultimately, all those super dense formulas in API 520 Part 1 really just boil down to this. You take the required flow rate and you multiply it by these specific correction factors. You've got KD, which is the effective coefficient of discharge, KB, which corrects for back pressure that might be pushing against the valve, KC, which is a capacity correction if a rupture disc is installed below the valve, and the Reynolds number, which is incredibly crucial for accounting for the viscosity of thick, sticky liquids. Once you apply all these factors, the equation spits out the final required discharge area. That minimum required area is what guarantees the valve is physically large enough to save the vessel. Okay, Section 4, Rules for Safe Installation. Piping the path. Because having a perfectly sized valve is completely useless if it's installed improperly. So let's shift our focus to the crucial piping that connects the valve to the tank, referencing API 520 Part 2. In a true gold standard installation blueprint, you will usually see two pressure relief valves installed side by side. This provides 100% spare relieving capacity. Right below the valves, you'll see isolation block valves. By using strict administrative controls to manage these block valves, operators can actually isolate one relief valve, take it completely off the tank for testing and maintenance, all while the second valve remains fully active. So the tank is never, ever left unprotected. Let's actually trace the fluid's escape journey during an emergency. It originates down in the vessel, then travels up the inlet piping. Now, this inlet piping is critical. It must be strictly managed, kept extremely short and wide. If there's too much friction or a sudden pressure drop in that inlet pipe, the valve will open, the pressure in the pipe will plummet, the valve will slam shut, and then the cycle repeats almost instantly. This is a phenomenon called valve chatter, and it is so violent it can literally tear the piping apart. After successfully forcing open the valve, the fluid blasts through the discharge piping. This has to be routed perfectly to avoid creating any low spots or liquid traps where fluids could pool and block the flow. And speaking of that discharge piping, engineers must always beware of back pressure. There are two main types to worry about here. First, superimposed back pressure, which is pressure that's already existing in the discharge pipe before our valve even opens. And second, built-up back pressure, which is the pressure created by the explosive release of the fluid itself.
If the discharge pipe is too small or routing is too long, this back pressure can actually push back down against the top of the valve disc, effectively defeating the entire safety system and preventing the valve from relieving the tank. It's a huge hazard.
And finally, Section 5, Disposal, Flares and Drums, the Aftermath. Okay, so our valve is opened, the math was spot on, the piping held together, and the tank is safe. But that introduces the final stage of the journey. Once thousands of pounds of boiling, dangerous fluid escape the tank, where does it safely go? I mean, you obviously can't just dump it out into the employee parking lot. Releasing raw, highly toxic gas directly into the air is incredibly dangerous. So plants usually use giant combustion flare systems to safely burn the vapors, converting them into much less objectionable compounds. But designing a flare, as detailed in API 521, is highly complex. Engineers have to calculate the safe dispersion of the plume. They have to measure thermal radiation to ensure the intense heat from the giant flame doesn't melt nearby equipment or worse, harm personnel. They must mitigate the roaring noise, design ultra-reliable pilot ignition systems, and most importantly, they absolutely must utilize knockout drums to remove any liquid before it ever reaches the flame.
And just how big do you think these knockout drums need to be? 20 to 30. That number right there represents the exact minutes of emergency liquid flow that a main flare knockout drum is staggeringly scaled to hold safely. Flares are designed to burn gas, right? Not liquid. If a massive slug of raw liquid hits the flare tip, it can literally rain flaming droplets down onto the plant below. To prevent this nightmare scenario, the knockout drum acts as a massive speed bump, completely separating the liquid from the gas and holding up to half an hour's worth of catastrophic emergency liquid flow.
Now, not all systems use flares. Some actually use atmospheric venting, releasing the gas directly into the air. But make no mistake, neither option is just a simple open pipe. Both require intense, rigorous engineering to prevent hazards. Flare disposal relies on combustion, but requires that massive upstream liquid separation we just talked about. Atmospheric venting, on the other hand, skips the flame entirely, but because the toxic vapors aren't being burned away, it requires incredibly strict droplet size control and advanced dispersion analysis. They have to guarantee that a hazardous, completely invisible rain doesn't just fall down onto working areas or neighboring property.
Wow, okay, we've covered a tremendous amount of ground today in this explainer, from the terrifying causes of overpressure to the intricate mathematical sizing of the valves, and finally, to those massive flare systems that neutralize the ultimate threat. So I want to leave you with this thought. Next time you drive past a refinery or a chemical plant and you see that big flame burning high up in the sky, will you just see pollution, or will you see an expertly engineered, meticulously calculated safety system actively doing its job, safely managing energy balances and preventing a massive, catastrophic disaster? Thank you so much for joining me on this explainer. Keep learning, and as always, stay curious.